Okay, sorry if there's any weird ambient noise going on here. I'm actually working away from home and away from my desk, but trying to get some things done. So here we go. We're doing a unit on derivatives of inverse functions at a particular point. Okay, so here's what's going on here. You got some function where it has an inverse. So let's say that function is y is the inverse function of f. Okay, then we get a rule here. The rule says the derivative with respect to x of that inverse at point x when x is equal to some value c is actually 1 over the derivative with respect to y of f of y when that function is equal to a, where f inverse of c is equal to a. So we need to look at this a little bit critically. What we're saying here is that I can find the derivative function at a particular value c. So the derivative of the inverse function at c by taking 1 over the derivative of the original function at some value a, so long as that when I take the inverse of f at c, I get a. So it's saying that at a particular point, I can find the derivative of the inverse without actually knowing how to write the inverse function. Okay, so another way of writing this notationally is to say that the inverse of c prime is equal to 1 over f prime of a, so long as f inverse of c is equal to a. So that's a lot going on there. We'll take a look at that. But we're not going to prove that as part of this course. It's a little bit beyond what we need for the BC exam. This is one of those things where you're just going to have to kind of accept it, commit it to memory. This is definitely something that I would put in your flashcard or Quizlet kind of reality here. Okay, so we're going to work through an example problem here. We're going to let f of x be equal to 3x squared minus x plus 7. And we want to find the derivative with respect to x of f inverse of x when x is equal to 9. Alright, so the game here is a little bit tricky. There's no really easy way to find the inverse of, that should be cubed. There we go. So change that to be cubed. There's no really easy way to find the inverse of this cubic function. So, I mean, you can try to sub the x and the y and solve for the x, but it's pretty much not going to work really easily. But we can figure out what f inverse of 9 is. Okay, so like, if you think about this, I want to have, like, say, 3a cubed minus a plus 7 is 9, right? Is 9. There should be an equals there, right? So this is the same as saying 3a cubed minus a minus 2 is 0. Now, rational root theorem, if there is a rational root to this, it has to be one of the factors of 3, which is either positive or negative 1 or 3, over one of the factors of 2, which would be positive or negative 1 or 2. So ultimately, if there is a rational root, it either has to be positive or negative 1, positive or negative 1/2, positive or negative 3, or positive or negative 3/2. So you can look through some of your pre-calc stuff and see how the rational root theorem works. And in fact, we do have a rational root here. If you try a equals 1, Well, you get 3 times 1 cubed minus 1 minus 2, which is 3 minus 1 minus 2, which is 0. Yay! Okay, so ultimately, f inverse of 9 is equal to 1. Okay, so that's a critical part of this problem. Alright, so we're going to use that fact to find the derivative of the inverse when x equals 9. Okay, so the using the formula above, we get the derivative with respect to x of the inverse of x when x is equal to 9 should equal 1 over the derivative with respect to y of f of y when y is 1. Alright, so if I look at f of x, well, f prime of x in this case is going to be 9x minus 1. So if I take f prime of 1, this should give me 9 minus 1, which is 9 minus 1, which is 8, right? So I want ultimately, so now I have like f prime of 1, right? So that's the f prime dy dx, or d, the derivative with respect to y of f of y, right? So that gets me that. So ultimately I have now that d dx of f prime of, or f inverse of x, right, when x is 9 should be 1 over f prime of 1, which should be 1 over 8, which means that I just have 1/8. Alright, so I have found the derivative of the inverse when x equals 9. It might take you a little bit to kind of grasp what's going on here. I would advise kind of running back and forth through some of this video to make sure that you're fully comprehending the example. But we do have a second topic in this, which is going to be the idea of using logarithmic differentiation. Alright, so logarithmic differentiation is a way of taking a derivative or setting up kind of like predisposing a function so that it's easy to take the derivative of. Okay, so usually this is used when you have some function of x that is a composition where you have f of x and then you're taking that to some other expression of x. Basically, the tip-off that you're doing logarithmic differentiation is that there's an x in the power of the expression that you're trying to take the derivative of. Alright, so the best way to kind of look at this is there's a set of rules here. One is you tend to take the natural log of both sides of an equation, and then you ultimately use the power rule for logarithms. So what that does is it gives you the ability to take that exponent, that g of x exponent, and move it in front of the logarithm as a coefficient. And we'll see that in a minute in our example. And then ultimately you use implicit differentiation to find dy dx. Okay, so it's a pretty simple, straightforward thing. It just gets you out of the block of having the power in the, or the variable in the power, and it's a way around that problem. Okay, so let's look at an example of logarithmic differentiation. Let's say we want to find the derivative with respect to x of x to the 2x plus 3. Okay, so this is where we have the problem, because this expression up here is changing with the x. So that's what's driving our issue. So according to this, I want to let y be equal to that function, x times 2x plus 3, and then we take the natural log of both sides. So I take the natural log of x times 2x plus 3. That gives me a little bit of a tool here, right? So I can do some leverage. Because I have a natural log, I can bring that down in front as a coefficient. So the natural log of y is 2x plus 3 times the natural log of x. So now I've moved the power into a product. Okay, so that's not so bad, right? So what do I do here? I take the derivative of the left with respect to x is just going to be 1 over y dy dx. And then on the right, I take first, right, times the derivative of the second, plus, okay, the second, which is the natural log of x, times the derivative of the first, which is just 2, so that's going to give me 2 times the natural log of x. Okay, so I can do some rearranging here. I get 1 over y dy dx is, let's see, 2x plus 3 plus 2x times the natural log of x all over x. That means dy dx is going to be 2x plus 3 plus 2x times the natural log of x all over x times y. But we know what y is, because y is back here. So dy dx is 2x plus 3 plus 2x times the natural log of x all over x. So that's going to be x all over x. And then that's going to be times x to the 2x plus 3, right? Let's get that in there. 2x plus 3, right? But this x can cancel with one of those, so I can simplify to dy dx is equal to 2x plus 3 plus 2x times the natural log of y, or natural log of x, times x to the 2x plus 2, because I canceled that with one of those. Alright, so there we go. We got dy dx out of this. The method is take the logarithm of both sides. I mean, you can use a log of any base, but the natural log has an easy derivative. And then bring down the exponent using the power rule. And once you've done that, use implicit differentiation, and you should find your way out of the problem. Alright, so these are kind of like 2 off the beaten path examples that will show up on the BC exam. Again, thank you for putting up with the ambient noise in the background of this. Sometimes we got to work where we can. Alright, thank you.